Before we touch any code, let's step back and talk about what we are actually doing here. When we say exploratory data analysis or EDA, we're not just referring to plotting a few graphs. EDA is the process of understanding a dataset deeply, structurally, statistically, and contextually before building any model. It answers fundamental questions. What kind of data do we have? How many rows and columns? What types of variables? Are there missing values? Are there duplicates? Are there inconsistencies? What does the target variable look like? Are there outliers? Are there relationships between variables? At its core, EDA is about developing intuition. Before a machine can learn from the data, we need to understand it. If we don't understand the structure of the data, any model we build is essentially blind. Think of EDA as the diagnostic phase. It's like a doctor running tests before prescribing treatment. You wouldn't prescribe medication without examining the patient first. Similarly, you shouldn't build a predictive model without examining the dataset. A comprehensive EDA usually involves structural analysis, number of rows, number of columns, data types, data quality checks, missing values, duplicate records, inconsistent categories. Invariate analysis, distribution of each variable, central tendency, spread. Multivariate analysis, relationships between variables, correlations, group comparisons. The goal is not just visualization, the goal is understanding. Now let's talk about feature engineering. Feature engineering is the process of transforming raw data into meaningful inputs that a machine learning model can understand and use effectively. Models don't understand text, they don't understand dates, they don't understand categories, they understand numbers. Raw data is rarely model ready. For example, a date column might look useful, but until we extract year, month, or seasonality, it's just a string. A postcode might contain location information, but unless we encode it properly, it cannot be used in regression. A categorical variable with thousands of unique values can overwhelm a model if not handled carefully. Feature engineering bridges the gap between raw data and mathematical representation. In practice, feature engineering includes transforming variables, like log transforming skewed data, encoding categorical variables, creating new variables from existing ones, aggregating information, reducing dimensionality, handling high cardinality categories, preventing data leakage. It is both analytical and creative. It requires understanding the domain and understanding how models behave. Together, EDA and feature engineering form the foundation of any serious machine learning workflow. Without proper exploration, you risk misunderstanding your data. You risk introducing bias. You risk leakage. You risk building models that fail in production. And without proper feature engineering, even the most advanced model will underperform. In the next section, we'll start by looking at the dataset itself. We'll examine its structure, how many rows, how many columns, what types of variables, and we'll classify every column before we move further. Because understanding structure is the first step toward building something reliable. Now that we understand what EDA and feature engineering are, the first practical step is to understand the structure of the dataset itself, so that we understand what exactly are we working with. Let's take a look at the Google Colab notebook. We will be working with real UK housing data covering the period 2015 to 2024. This dataset contains transaction-level information about house prices across the United Kingdom, and the dataset we'll be using is UK House Prices 2015 to 2024 by Swarup Sudhulaganti on Kaggle. This is real-world data and not pre-clean and not simplified. Let's do the environment setup first. We will install the required libraries, Seaborn for statistical visualizations, scikit-learn for pre-processing and modeling. We will also import everything that we need later, NumPy and Pandas for data manipulation, Matplotlib and Seaborn for plotting, Standard Scaler for feature scaling, Ridge for regularized regression. We also configure plotting and display settings for clean output. Let's now execute the code block. When you see Setup Complete, you know your environment is ready. Next, instead of manually downloading the dataset from Kaggle and uploading it, we do it programmatically. That's how real production notebooks should work. We will use Kaggle Hub to download the dataset directly. Now, because Kaggle datasets can contain multiple files, we programmatically search for CSV files inside the downloaded directory. And finally, let's preview the data and ensure it has been successfully downloaded. Let's start with the size. This dataset contains 90,000 rows and 11 columns. Each row represents a property transaction. Each column represents a specific attribute of that transaction. In other words, we are working with 90,000 individual observations of housing sales. That's large enough to extract meaningful statistical patterns, but small enough to inspect thoroughly. Let's look at the first few rows. Immediately, we see the following columns: price, date, postcode, property underscore type, new underscore build, freehold, street, etc. At a glance, this tells us something important. Most of our variables describe location and property characteristics. Only one column, price, is purely numerical. That observation sets context for later. Now let's inspect the data types. This step is critical because the type of a variable determines how we analyze and encode it. As you see, price is stored as an integer. All other columns are currently stored as object types. Object type typically indicates text or categorical data. We will discuss categorical data type shortly. Notice something else. Each column has 90,000 non-null values. At first glance, this suggests the dataset has no missing values. However, this only tells us there are no explicit nans. It does not tell us whether there are hidden missing values represented as strings. That sets up later cleaning. Now that we know the structural properties, let's classify these variables conceptually. Quantitative variables. We have exactly one quantitative variable, price. This is a continuous numerical variable. It represents the transaction value of the property. Continuous means it can take any value within a range. For example, £200,000, £250,000, £250,001, and so on. The remaining 10 columns are categorical variables. These represent labels or groups rather than measurements, such as property characteristics, property underscore type, new underscore build, freehold. These describe characteristics of the property. Location variables: postcode, street, locality, town, district, county. These describe geographic information. Temporal variable: date. Although currently stored as text, this represents time. Once parsed, it becomes a powerful source of structured features. Now let's examine how many unique values each column contains. This is called cardinality. Cardinality matters because low cardinality variables are easy to encode. High cardinality variables can explode into thousands of features if handled improperly. This will strongly influence our feature engineering strategy later. So structurally, this dataset can be summarized as 90,000 observations, 11 columns, 1 continuous numerical variable, 10 categorical variables. Now that we understand the structure of the dataset, the next step is to validate its quality. We'll check for duplicates, hidden missing values, inconsistencies, because a clean structure is the foundation of reliable analysis. Before continuing our analysis, we need to clearly understand something fundamental. Not all variables are treated the same. In data science, how we analyze, visualize, and encode a variable depends entirely on its type. Broadly, variables fall into two main categories: quantitative variables, categorical variables. Quantitative variables represent measurable quantities. These are numeric variables with mathematical meaning. You can compute averages, calculate variance, measure differences, and apply mathematical transformations. Whereas categorical variables represent groups or labels rather than quantities. Unlike quantitative variables, categorical variables do not have arithmetic meaning, require encoding before modeling. Types of categorical variables. Categorical variables can be divided into three major types: nominal, ordinal, and binary. Let's go through each. Nominal variables. Nominal variables are categories without any inherent order. Examples: town, county. There is no ranking between categories. London is not mathematically greater than Manchester. They are simply labels. In our housing dataset, town, district, county, postcode, street, and property underscore type are nominal categorical variables. Ordinal variables. Ordinal variables are categorical variables with a meaningful order. For example, low, medium, high, bronze, silver, gold. Satisfaction rating 1 to 5. There is ranking, but the distance between categories is not necessarily equal. In our dataset, we do not have strong ordinal variables. Property type may appear ordered by price, but that ordering is statistical, not inherent. Binary categorical variables. Binary variables are a special case of categorical variables. They contain exactly two possible categories. For example, yes/no, true/false, 0/1. Binary variables are technically nominal, but they are simpler to encode. In our dataset, new_build and freehold are binary categorical variables. In summary, continuous variables might require scaling or log transformation. High cardinality nominal variables require advanced encoding. Binary variables can be encoded simply. Ordinal variables may require ordinal encoding rather than one-hot encoding. In our notebook, we only have one quantitative column, price. We have two binary categorical columns, new_build and freehold. And rest of the columns are nominal categorical columns such as property_type, postcode, street, etc. Now that we understand the structure of the dataset and the types of variables we are working with, we need to validate data quality. Data quality assessment is about identifying issues that could distort analysis or modeling. These include missing values, duplicate records, inconsistent formatting, and category inconsistencies. Let's examine each systematically. We begin by inspecting the dataset without changing anything. The dataset shows 90,000 rows, 11 columns, 90,000 non-null values in each column. At first glance, this suggests there are no missing values. But this only tells us there are no explicit NaN entries. It does not guarantee there are no hidden missing values. This distinction is important. In real-world datasets, missing values are often disguised. Instead of appearing as NaN, they may appear as empty strings, unknown, n/a, and none. So instead of trusting the info summary, we explicitly search for suspicious tokens. Here we examine several object columns and look at the most common values. We are checking for placeholders that represent missing information. Then apply replacement. After standardizing potential missing tokens into true NaN values, we reassess missingness. In this dataset, we observe that missing values remain negligible. That confirms structural completeness. This validation step is important. Even if nothing changes, we have verified integrity rather than assumed it. Next, we check for formatting inconsistencies. A very common issue in categorical data is leading or trailing whitespace. These appear identical to the human eye, but to a computer, they are distinct categories. We compare unique counts before and after stripping whitespace. If the number of unique categories drops, that means we had hidden duplicates caused by formatting. After stripping, in our dataset, we observe slight normalization. This step reduces artificial category inflation. Now we examine low cardinality categorical variables. These are variables like property_type new_build and freehold. Sometimes categories differ only by capitalization. For example, detached versus detached. These would be treated as different groups. After converting these categories to uppercase and standardizing spacing, we eliminate inconsistencies. Now we check for duplicate rows. Duplicate records can inflate patterns. If the same transaction appears twice, it will double its influence in the model. We detect 43 duplicate rows. That's small relative to 90,000, but still significant enough to remove. After dropping duplicates, we confirm that the dataset now contains 89,957 unique transactions. After systematic inspection, we conclude no significant missing values, 43 duplicate records removed, minor category normalization applied, whitespace inconsistencies corrected. The dataset is now structurally consistent and ready for deeper exploration. Now that the dataset has been cleaned and validated, we explore the target variable price. Before building any predictive model, we must understand how the target behaves, because if we misunderstand the target, we misunderstand the entire problem. Let's begin with descriptive statistics. So we have count, 89,957 observations. Mean price, approximately £323,892. Median price, approximately £244,995. Standard deviation, over £1.28 million. Minimum price, £100. And maximum price, £300 million. Now notice something important. The mean is significantly higher than the median. When the mean exceeds the median by a large margin, it suggests right skewness. That means there are extremely high values pulling the average upward. Then, the maximum value is £300 million. That is several orders of magnitude larger than the median. This indicates extreme outliers exist in the dataset. Now let's look at the highest and lowest recorded transactions. We observe multi-million pound properties at the upper end. These are likely luxury properties. Point at lowest values. At the lower end, we see extremely small values, including £100. These could represent special cases, perhaps land transfers or unusual transactions. Now let's visualize the distribution. We can clearly see that the distribution is heavily right-skewed. Most properties cluster in the lower price range. A long tail extends toward very high values. This type of distribution is common in housing markets. Property prices often follow a log normal-like pattern. Let's plot the box plot graph. We see a dense cluster of points, with many values extending far beyond the upper whisker. These are statistical outliers under the IQR definition. Using the interquartile range method, we calculate lower and upper bounds. We identify 5,077 observations beyond these bounds. That represents a significant number of high-value transactions. These values are legitimate transactions, but they will strongly influence linear models because linear regression is sensitive to extreme values. Instead of removing outliers, we optionally apply Windsorization. This caps extreme values at the 1st and 99th percentiles. Notice how the extreme tail becomes less dominant. Windsorization reduces the impact of extreme values without deleting observations. Now we apply a log transformation to price. Compare the raw histogram with the log transformed histogram. The distribution becomes far more symmetric. The extreme tail is compressed. The density spreads more evenly. Log transformation is particularly useful when the data is right-skewed. The variance increases with magnitude. Multiplicative effects dominate. In housing markets, price differences are often multiplicative rather than additive. A £50,000 difference means something very different for a £200,000 home than for a £2 million home. Log transformation helps normalize this behavior. From this exploration, what we have learned? The distribution of price is heavily right-skewed. Extreme outliers exist and influence the mean. Median is more representative than mean. Log transformation stabilizes the distribution. These insights directly inform our modeling strategy. We will model log price instead of raw price. That is the key modeling decision. We've explored the target variable. Let's now move to one of the most powerful dimensions in housing data: time. Property markets evolve. Prices change year to year. Seasonality exists. Economic cycles influence transactions. But right now, our date column is just text. And as long as it's a string, we cannot extract meaningful temporal information. A string date is not usable for modeling. We now convert the date column into a proper date-time format. This will allow us to extract year, extract month, extract quarter, extract day of week, sort chronologically, and compute time differences. After conversion, the date time changes to date time. Now the column has temporal structure. From the past date, we extract year, month, quarter, day of week, and is weekend. Year. Year allows us to capture long-term market trends. Month. Month allows us to capture seasonality. Quarter. Quarter aggregates months into broader economic segments. This can help capture macroeconomic cycles. Day of week. Day of week captures micro patterns in transaction timing. While this may not heavily influence price, it adds structural temporal context. And weekend flag is weekend converts day of week into a binary feature. Binary features are simple, interpretable, and model-friendly. We also create a linear trend variable, years since 2015. Explain. Instead of modeling year as categorical, we model it as a continuous time progression. This allows linear models to capture long-term upward or downward trends. Months and days of the week are cyclical variables. December and January are neighbors. Sunday and Monday are neighbors. But if we encode month as 1 through 12, the model sees December 12 and January 1 as far apart. That's incorrect. Solution: sine and cosine encoding. To preserve cyclical structure, we encode month using sine and cosine transformations. This maps months onto a circle. Imagine the months arranged in a circle. The sine and cosine representation captures position on that circle. Now December and January are close in feature space. Do same for day of week. We apply the same logic to day of week. This is an advanced but highly effective technique for cyclical data. We now have the following time-based features: year, month, quarter, day of week, is weekend, years since 2015, month, sin month, cause DAO sin, and DAO cause. These features transform raw timestamps into structured numerical signals that models can interpret. Now let's aggregate the data by month. We compute count of transactions, mean price, median price. This allows us to visualize long-term market trends. Here we see the monthly median house price over time. We observe a clear upward trajectory. There are fluctuations, but the overall trend is increasing. Median is robust to outliers. It reflects the typical property transaction. Now we examine the monthly mean price. Notice how the mean occasionally spikes more dramatically than the median. This suggests luxury property transactions are influencing the average. When mean diverges from median, it indicates extreme high-value transactions in that period. From this time-based exploration, we learn the housing market shows a strong upward trend. The mean is more volatile than the median. There is evidence of seasonality. Time is likely a powerful predictor of price. Therefore, time-based features should be included in our modeling pipeline. We have successfully transformed a simple text column into a structured temporal feature set. We've analyzed the target variable. We've engineered time features. Now we examine how price behaves across categorical groups. In housing data, categorical variables often carry strong predictive signal. Property type, ownership status, and location categories can significantly influence transaction value. First, we examine how many observations exist in each category. For property underscore type, we observe categories such as detached, semi-detached, terraced, flat, other. It's important to understand category frequency. If a category has very few observations, its statistical estimates may be unstable. Then move to, for new underscore build, we see two categories, yes, no. This is a binary categorical variable. Then, for freehold, again, yes, no, another binary categorical variable. These binary variables are simple, but they often carry meaningful economic information. Now we examine how price varies by property type. Detached properties show the highest median price. Semi-detached properties fall below detached. Terraced properties fall further. Flats tend to cluster at the lower end. This confirms an intuitive hierarchy. Property type strongly influences price. Important nuance. However, the box plot also shows wide spreads and extreme outliers. This reflects price variability within each category. Now we repeat the analysis using log transformed price. Notice how the distributions appear more compact. The extreme skewness is reduced. The separation between categories becomes clearer. The log scale allows us to compare proportional differences rather than absolute differences. This often provides better modeling stability. Now we examine whether new builds command a premium. We observe that new build properties generally have a higher median price compared to non-new builds. This suggests a potential new build premium. However, we must remember that price differences may also be driven by location and property type. This is univariate analysis. It does not control for other variables. That shows sophistication. Now we examine ownership structure. Freehold properties appear to have higher median prices compared to leasehold properties. This is economically intuitive. Freehold ownership often commands a premium due to full property ownership rights. Again, however, this is descriptive analysis, not causal inference. From this categorical analysis, we observe property type strongly influences price. Detached properties command the highest median prices. New builds tend to be priced higher. Freehold properties appear more valuable than leasehold. These categorical variables clearly contain predictive signal. This validates the importance of proper encoding later. So far, we've analyzed the target variable, temporal trends, property characteristics. Now we turn to perhaps the most important factor in housing data, location. In real estate, location is often the dominant driver of price. However, our dataset currently contains full postcodes, and full postcodes are extremely granular. Let's look at the raw postcode column. Each postcode contains highly specific geographic information. In the UK, a full postcode can identify a small group of addresses, sometimes even a single building. This level of granularity is too detailed for direct modeling. If we one-hot encode full postcodes, we could end up with thousands of unique features. That would increase dimensionality, increase sparsity, increase computational cost, and risk overfitting. First, we standardize postcode formatting. We convert to uppercase and remove whitespace. This ensures consistent parsing. Without standardization, parsing rules could fail or create inconsistent categories. Now we extract the postcode area. The postcode area corresponds to the first one or two letters. For example, S, W, B, M, L, S, etc. The postcode area represents a broad geographic region. It captures city level or regional information. This dramatically reduces cardinality while retaining macro location signal. Next, we extract the postcode district. This includes the area plus one or two digits. For example, SW1, B15, LS10, etc. The district is more granular than area, but far less granular than full postcode. It captures neighborhood level information. Now let's compare original postcode, extracted postcode underscore area, extracted postcode underscore district. Notice how we have decomposed a highly specific string into structured geographic features. Instead of potentially tens of thousands of unique postcodes, we now have a manageable number of postcode areas, a moderate number of postcode districts. This makes modeling feasible. High cardinality categorical variables are dangerous if handled incorrectly. One hot encoding full postcodes would create thousands of columns, increase sparsity, risk overfitting, reduce generalization. By extracting area and district, we preserve meaningful geographic signal while controlling dimensionality. This is what feature engineering does and required for. We now have multiple geographic layers: county, broad region, district, sub-region, town, localized region, postcode area, macro geographic, postcode district, neighborhood level. These layers allow us to capture hierarchical location effects. Later, we will encode these layers carefully using frequency and target encoding instead of naive one-hot encoding. We've cleaned the data, we've engineered features, we've extracted geographic structure. Now we are ready to prepare for modeling. But before we build any model, we must decide how to split the data. And this decision is critical. A very common approach in machine learning is to randomly split the dataset into 80% training, 20% testing. That approach works well for many problems, but for time-based data, it can introduce a serious issue: future leakage. So, what is leakage? Data leakage occurs when information from the future influences the training process. In housing markets, prices evolve over time. If we randomly mix 2024 data into the training set while evaluating on 2022 data, we allow the model to learn from the future. That produces artificially optimistic results. A model that performs well with leakage may fail in real-world forecasting. The first step is to ensure the dataset is sorted by date. Time-based splitting requires chronological order. We are now respecting the temporal structure of the data. Next, we define a cutoff year. In our case, training data 2015 to 2022, test data 2023 to 2024. Pause. This simulates a realistic scenario. We train the model on historical data and evaluate on future data. We now create train data frame for years less than or equal to 2022, test data frame for years greater than 2022. Let's verify. Training data spans 2015 to 2022. Test data spans 2023 to 2024. We also observe 81,467 rows in training, 8,490 rows in testing. The majority of data is used for learning. The most recent years are held out for evaluation. This split is called production safe because it mimics how models are deployed in the real world. In reality, we train on past data. We predict future outcomes. We never have access to future information during training. This preserves causal direction. In high cardinality categorical variables, many categories appear only a few times. Why rare categories are a problem. When a category appears very infrequently, it creates several problems: statistical instability, overfitting risk, unreliable target encoding, and sparse feature expansion. For example, if a particular street appears only twice, any encoding derived from it will be based on extremely limited information. That signal is unreliable. First, we inspect the number of unique categories in our high cardinality variables using only the training dataset. We must compute this using training data only. We never use test data to determine grouping logic. Before grouping, we observe very high unique counts, particularly in street, postcode, district, and town. These numbers confirm high granularity. We define a minimum frequency threshold. In our case, categories that appear fewer than 50 times will be grouped into a single category labeled Other. The threshold is somewhat heuristic. The goal is to remove categories that do not provide statistically reliable patterns. Categories that appear often retain individual identity. Rare categories are pooled. We apply grouping to town, district, county, street, postcode area, and postcode district. The rare categories are identified using training data, and then the same grouping rule is applied to test data. This ensures consistency without leaking test information into training. After grouping, we observe a reduction in unique categories. The dimensionality is now significantly more manageable. This step dramatically reduces sparsity while retaining the majority of geographic signal. By grouping rare categories, we reduce noise. We reduce overfitting. We improve statistical reliability, and we make encoding more stable. Especially for target encoding, small sample sizes can produce extreme values. Grouping prevents that instability. The next step is to convert these categorical variables into numeric representations. The first encoding strategy we apply is called frequency encoding. What is frequency encoding? Frequency encoding replaces each category with the number of times it appears in the training data. For example, if a particular town appears 2000 times, every row belonging to that town will receive the value 2000. Instead of representing the category itself, we represent how common it is. Frequency often captures important structural information. In housing data, popular towns tend to have many transactions. Major districts may behave differently than small ones. Frequency encoding indirectly captures market activity level, density, and regional importance. It reduces high cardinality categories into a single numerical column that is computationally efficient. Before encoding, these columns contain strings: town, district, county, street, postcode, area, and postcode, district. These strings cannot be used directly in regression models. We must convert them into numeric form. We compute value counts on the training dataset only. This produces a mapping, category to count. This mapping is then applied to training data and test data. The test data does not influence the frequency mapping. It simply receives the frequencies learned from training data. After applying frequency encoding, we now have new columns: town frequency, district frequency, county frequency, street frequency, postcode, area frequency, and postcode district frequency. Each row now contains a numeric representation indicating how common its category is in historical data. A larger frequency value indicates a more common category, a denser market region, and possibly more stable pricing patterns. A smaller frequency value indicates a rarer category, less transaction data, and potentially higher variability. Frequency encoding is computationally efficient, handles high cardinality variables well, does not explode dimensionality, captures density information. However, frequency encoding does not directly capture price behavior. It only captures how common a category is. It does not tell us whether a town is expensive, only whether it is frequently observed. To capture price behavior, we need a more powerful encoding strategy. Now we move to a more powerful technique: target encoding. This method directly incorporates information from the target variable into categorical features. But it must be implemented carefully. If done incorrectly, it introduces severe data leakage. Target encoding replaces each category with the average value of the target variable for that category. In our case, for each town, district, or postcode area, we compute the average log price in the training data. So instead of representing London as a string, we represent it as the typical log price observed in London. That's powerful. Target encoding directly captures price behavior. It tells the model, this town tends to have higher prices. This district tends to have lower prices. It embeds domain knowledge into the feature itself. In housing markets, location is one of the strongest predictors of price. Target encoding allows us to capture that efficiently. The danger arises when we compute averages using the entire dataset. If we calculate the mean log price for each town using both training and test data, we leak future information into the model. The model would effectively know the average future price of each category. That would inflate performance artificially. We compute global mean of log price, mean and count per category. These statistics are derived exclusively from historical data. Then, we create a mapping, category to smoothed average log price. If a category appears very few times, its average price may be unstable. For example, if a town appears only twice and both transactions were luxury homes, its mean price would appear artificially high. That would mislead the model. The solution: smoothing toward the global mean. To reduce instability, we apply smoothing. We combine the category mean, the global mean, weighted by how many observations the category has. Categories with many observations rely mostly on their own mean. Categories with few observations are pulled toward the global average. This prevents extreme values from small samples. We now apply the smooth mapping to training data, test data. The test data does not compute its own means. It only receives the mapping learned from training data. If a test category was never seen in training, it defaults to the global mean. That ensures stability. We now have new columns such as county, district, town, postcode area, and postcode district. These features directly represent the typical log underscore price associated with each geographic category. After this step, we have reduced high cardinality location variables. We have captured density via frequency encoding. We have captured price behavior via target encoding. We have prevented leakage. We have now cleaned the data, engineered temporal features, reduced high cardinality variables, applied frequency encoding, applied target encoding. The next step is to assemble everything into a final modeling table. This is where feature engineering transitions into modeling preparation. First, we define the numeric features we want to include. These include time-based features: year, quarter, is weekend, year since 2015, month, sign, month, cause DAO, sign DAO, cause, frequency encoded features, and target encoded features. These are all numeric columns ready for modeling. Notice that the original raw categorical columns are not included here. Only their engineered numeric representations are used. Next, we identify low cardinality categorical variables: property type, new build, and freehold. These variables have few unique values. Therefore, we can safely apply one-hot encoding without exploding dimensionality. Before assembling the final table, we inspect a small preview of the selected columns. This ensures we are combining the correct features. Everything looks numerically structured and consistent. We now apply one-hot encoding to property underscore type, new underscore build, and freehold. One-hot encoding creates binary indicator columns. For example, property type detached, property type flat. Each row will have a 1 in the corresponding category column. This allows the model to treat each category independently without introducing artificial ordering. After one-hot encoding, we align the categorical feature columns between training and test sets. Sometimes a category appears in training but not in test, or vice versa. Alignment ensures both datasets have identical column structure. Any missing category in test is filled with 0. This preserves consistency. We now concatenate numeric engineered features, one-hot encoded categorical features. This produces x underscore train, x underscore test. At this stage, every feature is numeric. The model can now process this matrix directly. The target variable is log price. We assign yTrain equals training log price, yTest equals test log price. We model log transformed price for stability and reduced skewness. Finally, we inspect the shape of the feature tables. We observe X-train 81,467 rows, 28 features. X-test 8,490 rows, 28 features. Both training and testing sets now have identical feature dimensions. This confirms correct construction. Before we train the model, we take one final analytical step: multivariate analysis. Up until now, we've examined variables mostly in isolation. Now we examine how they relate to each other. Specifically, we look at correlation. This heat map shows the pairwise correlations between all engineered features and the target variable. Correlation values range between -1 and 1. 1 means perfect positive relationship, -1 means perfect negative relationship, 0 means no linear relationship. Notice that target encoded geographic features show strong positive correlation with log price. Time-based features like year or years, underscore since, underscore 2015 likely show positive correlation, and frequency encodings may show weaker or mixed relationships. This confirms that location and time are major drivers of price. Let's now isolate correlation with log price. Here we can clearly see which features have the strongest linear relationship with the target. Typically, we observe target encoding features among the strongest predictors, year-based features showing upward trend, and some one-hot encoded property types contributing signal. But correlation analysis is not only about target relationships. It also reveals multicollinearity, meaning features highly correlated with each other. Notice that town T, district T, and postcode area T are likely correlated. Year and years since 2015 are perfectly correlated. These relationships introduce redundancy. And this is precisely why we selected ridge regression. Ridge regression penalizes large coefficients. When features are correlated, ordinary linear regression can produce unstable estimates. Ridge distributes weight more smoothly across correlated features. If we were using a tree-based model, multicollinearity would matter less. But for linear models, it is crucial. From this analysis, we learn location-based target encodings carry strong signal. Time trend is significant. Some engineered features are redundant. Regularization is justified. The feature engineering decisions we made earlier are validated by this correlation structure. We've cleaned the data. We've engineered features. We've built a production-safe train-test split. Now, we finally train a model. But before fitting the model, we must address one final pre-processing step: feature scaling. Our feature matrix contains variables on very different scales. For example, frequency counts may range into the thousands. Target encoding values are small decimals. Sine and cosine features range between -1 and 1. Linear models are sensitive to scale. If features are not scaled, variables with larger magnitude can dominate the regression coefficients. We now apply a standard scaler. It transforms each feature to mean equals 0, standard deviation equals 1. Important emphasis: the scaler is fit on training data only. The test data is transformed using the same parameters. This prevents information leakage. We use ridge regression, which is a linear regression model with L2 regularization. Ridge regression penalizes large coefficients. It helps prevent overfitting, especially when features are correlated. In our dataset, many engineered features are related. For example, town to district and postcode area to. Regularization helps stabilize coefficient estimates. We now train the ridge regression model using scaled training features. The model learns a linear relationship between engineered features and log price. Next, we generate predictions on the test dataset. Remember, this data represents future years that were not used during training. This is a realistic evaluation scenario. We compute mean absolute error, root mean squared error in log space. Log space error reflects proportional differences rather than absolute pound differences. For example, an error of zero point 0.3 in log space roughly corresponds to about a 30 to 35% relative difference. Log error is mathematically convenient but not intuitive for stakeholders. To interpret results in practical terms, we convert predictions back to pounds. We apply the inverse log transformation. Now, predictions represent actual estimated property prices. In real price terms, we observe MAE around £122,000, RMSE around £303,000. Now interpret carefully and honestly. The median house price in our dataset is approximately £245,000. An average absolute error of £122,000 means the model's prediction is off by roughly half the median value. That tells us several things. The housing market is highly complex. Location effects are strong but non-linear. A simple linear model has limitations. Then, RMSE is larger than MAE, which suggests some large prediction errors remain, likely influenced by luxury properties. Ridge regression serves as a baseline model. It confirms that our feature engineering pipeline works, no leakage exists, evaluation is realistic. But it also highlights the need for nonlinear modeling, potential interactions not captured by linear regression. The most important takeaway is not the error value itself, it is the integrity of the process. We cleaned the data carefully, prevented leakage, engineered meaningful features, evaluated realistically. That is what makes this workflow production ready. This completes our end-to-end EDA and feature engineering pipeline, from raw housing data to a structured production-safe modeling framework. In the next stage, we can experiment with more advanced models and compare performance.